This week's lesson will be a review of the Pythagorean theorem. Now recall that a right triangle is a triangle with one right angle. The side opposite the right angle is called the hypotenuse. The other two sides are called legs. In the figure to the right, the legs have been labeled leg 1 and leg 2. Now the sides are often referenced using the variables a, b, and c, where a and b represent the length of the two legs and c represents the length of the hypotenuse. The Pythagorean theorem is a statement about the relationship between the sides of a right triangle. It states that the square of the hypotenuse equals the sum of the square of the other two sides, or legs, of the triangle. So, for example, the hypotenuse of this triangle, if we squared that value, it would be equal to the square of leg 1 and leg 2 added together. Now, using our variables, this is most often written as a squared plus b squared equals c squared, where a and b represent the two legs, and it doesn't matter which one is which, all right? And c represents the hypotenuse. In example 1, we'll use the Pythagorean theorem to find the length of a missing side. In the following triangle, the two legs are known, 4 units and 3 units. The hypotenuse is unknown. So using the Pythagorean theorem, we can fill in our known values to solve for our unknown values. The values of a and b are 3 and 4, and the value of c is unknown. So I plug in 4 for one leg, 3 for another, and I'll use the variable x to represent that the hypotenuse is unknown. So I'll simplify 4 squared and 3 squared. That gives us 16 and 9, the sum of which is 25. To find the value of x now, we have to take the square root of both sides. The square root of x squared is just x, and the square root of 25 is 5. So the length of the hypotenuse in this right triangle is 5 units long. In example 2, we'll do the same thing, but notice the unknown side is no longer the hypotenuse, it's one of the legs. Now, keep in mind that not all square roots are rational. Most, in fact, are irrational. So in this case, we're going to round our answer to the nearest tenth. So let's set up our Pythagorean theorem and see what we've got. So one of the legs is unknown, and the other leg is known. So we're going to fill in x for a and 10 for b, and then our hypotenuse is also known, so we can plug in 15 for c. So that gives us x squared plus 10 squared equals 15 squared. Simplifying, we get x squared plus 100 equals 225. Solving for x, we first subtract 100 from both sides, and then we take the square root of both sides. And that gives us the square root of x squared is x, and the square root of 125 is going to be an irrational number, so we are going to approximate it by rounding to the nearest tenth, and that's approximately 11.2 units. Now, since the Pythagorean theorem only applies to right triangles, it can also be used to identify triangles that contain right angles. So let's see if this makes sense. If we have a right triangle, then a squared plus b squared must equal c squared. So if a squared plus b squared does not equal c squared, that means we're not dealing with a right triangle. Let's check this first example. Here we have one leg is 12, the other leg is 5, and the hypotenuse is 13. Plugging those values into the Pythagorean theorem, we get 12 squared plus 5 squared equals 13 squared. Simplifying both sides gives us the equation 169 equals 169. So this is a true statement. So a squared plus b squared does equal c squared, therefore this is a right triangle. Why don't you try the next two on your own and see how you do? Pause the video now. All right, let's see what you came up with. So setting up our second triangle, 8, 6, and 9 would give us 8 squared plus 6 squared equals 9 squared, which simplifies to 100 equals 81. That is not true, so this cannot be a right triangle since the Pythagorean theorem applies to all right triangles. So this third example shows you it doesn't matter how complex the values are. This technique can be used for any type of right triangle. So plugging in these values into the Pythagorean theorem gives us 2.1 squared plus 7.2 squared equals 7.5 squared. And simplifying both sides, we get 56.25 equals 56.25. So this is a right triangle. Now, in today's assignment, you're going to have a skills assignment and a performance assignment. A performance task. So in order to do well on the performance task, you need to do well on the skills assignment. There are 3 parts to the assignment. You're going to find the distance between 2 points. You're going to solve real-world problems involving right triangles. And then you're going to solve problems involving 3-dimensional figures. So what I'd like you to do is continue watching the video. I go through 3 examples illustrating how to accomplish each of these 3 basic skills. Okay, in our first example, we're going to explore how you can find the distance between 2 points. So here we have a point at -2, 3, and another point at 5, 7. And we want to find the distance between them, and that can be represented by a straight line between those 2 points. So one technique is to create a right triangle from these 2 points on the coordinate plane. So we're going to move up from y equals 3, 1, 2, 3, 4 units to y equals 7. So the length of this line segment is 4 units. Now we're going to move from x equals -2 over 1, 2, 3, 4, 5, 6, 7 units to x equals 5. So this would be 7 units. The length of this side would be 7 units. And since the coordinate plane is already set up in a grid that makes 90-degree angles, we know that this angle right here is a right angle. So now we have a right triangle. So we can use the Pythagorean theorem to find the distance of this unknown side, the hypotenuse, which we're going to call d for the distance between the 2 points. So let's set up the Pythagorean theorem. So one leg is 4 units long, so we're going to square that. The other leg is 7 units long, so we'll square that. And that should be equal to the hypotenuse, or the distance between the 2 points, squared. So 4 squared is 16. 7 squared is 49. And the sum of 16 and 49 should equal d squared. So that sum is 65. And if we wanted to find d at this point, we take the square root of both sides. Now the square root of d squared is equal to d. And the square root of 65 is an irrational number, so we could round that if needed. But for right now, we're going to keep it in its simplest form, the square root of 65. I should say its most precise form, not its simplest form. And we can just rewrite this so it reads left to right. The distance between the 2 points is equal to the square root of 65 units. In our second example, we're going to explore how to take a problem in the real world and solve it using the Pythagorean theorem. Now above is a description of a real-world situation. Now you can either visualize this in your head, or as discussed in class, I suggest drawing a picture to help visualize the different parts of the right triangle. So let's read through the description. The bottom of a ladder must be placed 3 feet from a wall. The ladder is 12 feet long. How far above the ground does the ladder touch the wall? So let's see, if I wanted to visualize this, I might draw a wall. Here's our wall. All right, the ladder is 12 feet long. So I'm going to draw a ladder, and it goes on the wall. Here's our ladder. And the length of the ladder is 12 feet. And it says that the ladder must be placed 3 feet from the wall. So the base of the ladder has to be 3 feet from the wall. So this distance, this distance right here has to be 3 feet. And we want to know how far above the ground does the ladder touch the wall. So basically we want to know what's this point right over here. Where does the ladder touch the wall? So I'm sure you can identify the right triangle in this situation. Here's the ground, there's the wall, and the wall makes a right angle with the ground. We have a hypotenuse, the length of the ladder, which is 12 feet, and we have one side, or one leg, which is 3 feet. So, using our Pythagorean theorem, we've got a squared plus b squared equals c squared. And let's fill in our values. 12 is our hypotenuse, so that'll be 12 squared equals, one of the legs is 3, so that's going to be 3 squared. And the other leg, the height of the ladder on the wall, is unknown, so we'll leave that as a squared. And now we can begin to simplify and solve. A squared plus 9 equals 144. Solving for a, we get a squared equals 144 minus 9, which is 135. And then, of course, to solve for a, we're going to take the square root of both sides. And so the value of a would be the square root of 135. In our third example, we're going to use the Pythagorean theorem to help solve problems involving three-dimensional figures. So let's look at the following situation. We need to find the length of d in the figure below. Here's the length d. It goes from one point in the rectangular prism, to another point on the opposite side. All right. We know that a, the length a, is equal to 8. Length b is equal to 5. And length c is equal to 3. And we're going to round our answer to the nearest tenth. So we need to find length d. Now, if you notice, all right, length d goes from one side of the rectangular prism to the other. It's the diagonal of the prism. So how are we going to use the Pythagorean theorem to find this length? So if we're going to use the Pythagorean theorem, we've got to find a right triangle. So here we have a diagonal. All right, this diagonal goes down line segment C, and it goes down to the base of the prism. And now if we connect these 2 points from here to here, well, because the prism goes straight up, this forms a right angle. And there's our right triangle right there. So in order to find length d, all we need to know is the lengths of this leg and that leg right over there. The problem is we don't know the length of this leg, but we can find the length of this leg if we look at the base of the prism and notice that that segment forms another right triangle. So we're going to have to use the Pythagorean theorem twice here. Once to find the length of this segment, and then once we know that length, we can use that segment in this other calculation. So let's find the length of this segment, which in this triangle happens to be the hypotenuse. So here we have a leg that's 8 units long, another leg that's 5 units long, and an unknown hypotenuse. So that would be 8 squared plus 5 squared equals an unknown length, c squared. So that's going to be 64 plus 25, which is equal to c squared. 64 plus 25 is 89. And then taking the square root of both sides, we get c equals the square root of 89. Now, notice it says round your answer to the nearest tenth. The problem is this isn't our answer. All we've done is we've found the length of this line segment, this diagonal along the base of the prism. which is going to be included or used in our second calculation to find the diagonal of the entire prism, line segment D. So now we can solve for length D using this other right triangle. So here we have, here's one leg, square root of 89, a second leg, 3, and we're going to try and find the hypotenuse, D. So we've got the square root of 89 is our first leg, and we're going to square that. Our second leg is 3 units long, and we're going to square that, and that should be equal to D squared. Now, the square root of 89 squared would be 89 because those are inverse operations. 3 squared is 9, and that gives us D squared. Now 89 plus 9 is 98 equals D squared. And so taking the square root of both sides, we get D equals the square root of 98. And the square root of 98 is approximately 9.8994, and that should be enough. It goes on to infinity. And we have to round it to the nearest tenth. Here's our tenth, so we look at the hundredths place. That's above a 5, so we're going to round this to, D is approximately 9.9 units. So we can say that D is approximately 9.9 units. Or, I'm sorry, the units in this case are inches. I forgot about that. 9.9 inches.